Okay, hello again. This is the second part of section 3.2 video. So if you did not see the first part, you need to go back to see the first part because this is a continuation of that. And again, I want to stay under 5 minutes, so let me get to this. All right, so note for that previous example, so on that last example on video 1, to get the other numbers in the equivalence class, you used repeated addition or subtraction. And so I talked about that already. All right, so something else to note is that when we work with multiple moduli, we can distinguish equivalence classes, and we do this by the following. One way to do this. Okay, so for example, Z3, we can denote as 0. This will be the equivalence class of 0. Let's see, we would say that would be the equivalence class for 0 mod 3. This would be the equivalence class for 1 mod 3 and 2 mod 3. Okay, and so we can write it like that because if we were talking about, say, Z6, then we wouldn't want to get confused because they represent two different equivalence classes. And I remember when we were doing Z mod M, when I was a student, my teacher used to tell us, in terms of, well, why is it 0, 1, and 2? Because since you look at 0 mod 3, or I should say in the equivalence class of 0 mod 3, negative 3 is in there as well. So, I mean, technically it wouldn't be wrong to state negative 3 mod 3 is equal to 0, the equivalence class of 0 mod 3. So these two are actually equal, and writing either way wouldn't be incorrect, but a way that my teacher used to tell us is that think of 0 as the captain. So 0 is going to be the captain of your team, and all your players are in this set. Okay, and so that's sort of the convention we use, and you'll see, I believe, on the next slide, why we use 0, 1, and 2 instead of using other numbers inside that equivalence class, inside that set of equivalence classes. Okay, but we can use this notation to distinguish between, again, 0, the equivalence class of 0 mod 6. As you can see below, they represent two different values. Okay, so we can use that, and you can use that notation. This notation can be used in general as opposed to using the bar over the top. So whichever one you want, just as long as you know the difference. And if you're using more than one equivalence classes at the same time, then you might want to use this notation right here. Okay. All right. Just looking at this, the whole modulo and congruency in terms of real world, we can actually go as far back as a clock. So this modulo, this is really called modular arithmetic, and this starts back in kindergarten. So you actually learn about this in kindergarten. And that's why math is so great, because you come back around full circle, and it's really great. Okay. And so if you think about the 12 hours on the clock, there's 12 hours on a clock. This is what we call, the clock represents mod 12. So that's why we don't say, that's why 13 o'clock is the same as 1 o'clock, because 13 is equal to 1 mod 12. And 14 o'clock is 2 o'clock, because 14 equals 2 mod 12. Okay, so I just wanted to keep that in mind. Now, the fact is this, and this is where it's coming all together in terms of why we use 0, 1, and 2 instead of other numbers in that equivalence class. Z sub m, so the equivalence classes of Z sub m, is always going to be the equivalence class of 0, 1, 2, ... all the way to m minus 1. And that's because this is connected to remainders, which is also called residue. That's something, if you take a higher level of math, you might see that term, or in different fields, you might see the term residue that refers to remainders. So this is in division when integers are divided by m. So notice in 3, if you take a number divided by 3, your remainder is either going to be 0, you're either not going to have a remainder, 1, or 2, because remember, if you get a remainder larger than 3, that means that number can go into 3 again, right? 3 can go into that number again, and so you would have to continue dividing until you get something smaller than 3. And so that's why Z mod m, or Z sub m, I'm sorry, refers to remainders, and that's why 0, 1, 2, ... to m minus 1 represents the equivalence classes, okay, because it's connected to the remainders. All right, and finally, theorem 3.23, I'm not going to write it down, but I want you to look in the book, write down those two, I think it's 2 parts to that theorem, kind of look through the proof. You don't necessarily have to write down the proof, but look through that proof and to see if you, and hopefully you can understand it, and now you can use those properties. Okay, so we're done. I'm a little over 5 minutes, but that's okay. We're going to, like I said on Monday, start the homework problems. There are more than one proof. I think I said it was only one proof. There's more than one proof, which is good because I really want you to get practice on equivalence relation. But I don't think it's too much. I think you guys will be working on that in class, and that should be great. Okay, so I will see everyone in class, and we are done with section 3.2.